Hi, I'm Doug Black. I'm editor-in-chief of Inside HPC. And today we're speaking with Mark Taylor of Sandia National Laboratories. He's a distinguished member of the technical staff, and he's involved in the E3SM MMF project, which is related to the Department of Energy's exascale computing project. And that's what we're going to talk about with Mark today. Mark, thanks for joining us. And if you would, please tell us a little bit about this research work that you're involved in.
So this is the ECP, DOE's exascale computing project funds a variety of applications. One of them is climate modeling or Earth system modeling. That's our project. I'm the principal investigator for the ECP part of that work. And it's in addition to or it's in support of a much larger DOE effort called E3SM, the Energy Exascale Earth System Model. And the goal of all those projects is a Earth system model that can run efficiently and well on DOE's upcoming exascale computing platforms. Hopefully to do simulations, the types of simulations that we couldn't do on conventional architectures. And then we also have a tie to DOE, an energy mission to look at Earth system climate issues related to the energy utilization and availability and things like that, how it interacts with climate change.
Okay, so clearly this is a ambitious, big picture kind of a project. As I understand it, you're looking at water resource and severe weather forecasting, how that impacts food supplies, food chains. Do I have that right?
We have the broader project has three major goals, and in the ECP, or this MMF multi-scale modeling project, we're focused on the water cycle. So doing a better job modeling the Earth's water cycle, and by that we mean like precipitation patterns over the continental US, regional details of the kind of long-term statistics of that. So frequency of droughts, floods, storms, how that impacts water availability, and then ultimately impacts, say, agriculture and energy production.
And I see that this project is developing a cloud resolving Earth system. What does that mean, cloud resolving?
Yeah, one of the key things we hope to do on these exascale machines is what we call cloud resolving. And that suggests resolving individual clouds, but what it actually means is resolving the overturning circulation, the convective motions that are responsible for cloud formation. So in a lower resolution model where you can't resolve those effects, you have to parameterize them or approximate, put in approximations for them. And they turn out to be quite important. And the approximations create a lot of uncertainty because they're never going to be exact. A lot of the biases in models are attributed to not being able to approximate these as good as we'd like to. So cloud resolving really resolves that key aspect of the climate system. And so we hope a cloud resolving model will have better, do a better job, especially at things like the water cycle, and have less uncertainty in the model. And the ECP project is basically two approaches to cloud resolving. One I refer to it as a brute force approach, which will be quite expensive, but it's very natural for exascale architectures. And then we're also exploring this multi-scale approach called superparameterization, which will hopefully let us on exascale machines capture some aspects of a cloud resolving model, but at much faster throughput, so it can make the kind of century-long simulations needed for climate and Earth system studies.
Exascale caliber systems are still a year and a half away, or give or take. So what's the work you're doing now in advance of exascale compute power arriving?
So in the US and DOE, the two main exascale architectures are both GPU based. So we've been spending a lot of work porting our codes to GPUs, exploring different programming models and various approaches, and learning what runs well on a GPU, what doesn't run well. Really focus on, we don't want to run stuff that doesn't run as well on a GPU as it would on a CPU. So we really focus on these regimes like cloud resolving models, where the GPUs will provide a real benefit over a traditional CPU.
Now, I understand this work connects to DOE's biological and environmental research program. Is that the case? And maybe you could expand on that a little bit.
Yeah, the main E3SM project, the exascale energy Earth system model, is led by BER, or funded out of BER, the DOE BER office, and then the ECP office does a lot of the exascale, funds a lot of the exascale porting and readiness work in support of the E3SM project.
I see. And are there early indications of any the findings that you're anticipating, or maybe the advances that you're hoping to generate from out of exascale?
Yeah, so we're or my part of the project is really focused on getting the model running, and we haven't been running the model yet at these resolutions, or we've just started. But there's a lot of other effort in the community, especially in the regional modeling, where it's much more affordable. These are, I probably forgot to mention this at the beginning, but these are global models, so running the entire Earth. Regional models you can, of course, run at much higher resolution, where we can really see the advantages to not having to parameterize these convective processes.
Well, great work, Mark. And, we'll be looking for milestone announcements as you move forward, and especially once you all are up and running on exascale. So thanks very much for joining us today.
Oh, great. Thank you.